Ever wondered why proofs hold such a pivotal role in mathematics? They're not just a complex sequence of numbers and letters arranged to confound students. Proofs are the very lifeblood of mathematics, the solid foundation upon which the entire discipline stands. They are the rigorous checkpoints that guard the gate of mathematical truth, ensuring that no false statement crosses the threshold. Without proofs, it would be impossible to verify the validity of mathematical statements. We'd be adrift in a sea of uncertainty, unable to distinguish between fact and fallacy. Proofs also serve as a guide, illuminating the path to understanding complex mathematical concepts. They are the breadcrumbs left behind by mathematicians, leading us through the labyrinth of mathematical knowledge. Furthermore, proofs are vital for advancing the field of mathematics itself. They allow us to build upon the work of those who came before us, forging new paths in the vast wilderness of mathematical theory. Without proofs, mathematics as we know it simply wouldn't exist. Scene script. Let's delve into the first method, mathematical induction. Imagine you're climbing an infinite ladder. To reach the top, you need to take 2 steps. First, you must step onto the first rung. That's our base case. Second, you must prove that if you can step onto a rung, you can step onto the next one. And that's our induction step. Mathematical induction follows this same principle, allowing us to prove statements for all positive integers. Let's break it down. The base case is where we start, and it's usually the simplest case. For instance, if we are proving a statement for all positive integers, our base case is often when the integer is 1. Then comes the induction step, which is a little trickier. Here, we assume that the statement is true for a certain integer, let's call it k. Now, our goal is to show that if the statement is true for k, it must also be true for k plus 1. This is like saying, if we've managed to step onto the kth rung of our infinite ladder, we can also step onto the next one. To illustrate, consider the statement, the sum of the first and positive integers is n times n plus 1 divided by 2. Our base case when n equals 1 is straightforward to check. Now, for the induction step, we assume the statement is true for n equals sine ke. That is, the sum of the first k positive integers is k times k plus 1 divided by 2. We then need to prove that the statement also holds true for k plus 1. With a bit of algebraic manipulation, we find that it does. In this way, mathematical induction allows us to prove a statement for an infinite number of cases by proving just 2 steps. It's like saying, if you can step onto the first rung of an infinite ladder, and from any rung, you can step onto the next one, then you can climb the entire ladder. Mathematical induction, a powerful tool, allows us to prove a statement true for infinite cases by proving just 2 steps. Moving on, we explore proof by contradiction. This fascinating method of proof, also known as reductio ad absurdum, is like a thrilling detective story where we chase down a lie until it contradicts itself. Here's how it works. We begin by assuming the opposite of what we're trying to prove. We presume for a moment that our statement is false. Let's visualize this with a simple example. Suppose we want to prove that the square root of 2 is an irrational number. We start by assuming the contrary, that the square root of 2 is a rational number. Following this assumption, we'd arrive at a point where we're forced to accept that 2 equal integers are unequal, which is clearly absurd. This contradiction shows that our original assumption was false, and thus, the square root of 2 must indeed be irrational. Proof by contradiction, an elegant method, often helps us establish truth by illustrating the impossibility of the contrary. Next up is a straightforward approach, direct proof. This method is the bread and butter of mathematical proof techniques. It's simple, direct, and powerful in its simplicity. A direct proof involves using logic and mathematical rules to directly prove a statement. It's like building a bridge from one side of a river to the other step by step until you reach the other side. Let's illustrate this with an example. Suppose we want to prove that, for any 2 even numbers, their sum is always even. Sounds quite simple, right? But how do we prove this directly? First, let's understand what an even number is. An even number is any integer that can be written as 2 times another integer. So, we can express our 2 even numbers as 2 times some integers. Let's call these integers a and b. So, our 2 even numbers are 2 times a and 2 times b. Now we want to show that if we add these 2 numbers together, the result is still an even number. In other words, we want to prove that 2 times a plus 2 times b is an even number. We can use the distributive property of multiplication over addition to rewrite the sum as 2 times a plus b. Now, a plus b is an integer because the sum of any two integers is an integer, so 2 times a plus b is an even number because it's 2 times some integer, and there we have it. We've directly proven that the sum of any two even numbers is always an even number. We started with the definition of an even number, used some basic rules of arithmetic, and arrived directly at our conclusion. No detours, no assumptions, just a clear, logical path from start to finish. That's the beauty of a direct proof. It's a journey of logic, where each step is built on the firm ground of mathematical rules, leading us directly to our destination. It's like a mathematical roadmap, guiding our thinking and helping us make sense of complex ideas. Direct proofs, though simple, form the backbone of mathematical reasoning. They are the tools that allow us to explore the vast and fascinating landscape of mathematics with confidence and clarity. Now, let's turn our attention to proof by recurrence. This fascinating method is a powerful tool for proving statements that involve integers. It's like climbing a ladder, where each step depends on the previous one. But how does it work? First, you've got to establish a base case. This is like the first rung of our ladder. It's typically the simplest possible case, often involving the smallest integers. For instance, if we're proving a statement about positive integers, our base case could be the integer 1. It's our job to show that the statement is true in this specific case. Once we've got our base case, we then move on to the induction or recurrence step. This is where we assume that the statement is true for some arbitrary positive integer, let's call it n. This assumption is often referred to as the induction hypothesis. Now, here comes the dazzling part. We need to show that if the statement is true for n, it must also be true for n plus 1. If we can do this, we've successfully completed the recurrence step. This is like showing that if we're on one rung of the ladder, we can always reach the next. Let's put this into context with a simple example. Suppose we want to prove that the sum of all integers from 1 up to n is equal to n times n plus 1 divided by 2. Our base case, n equals 1, is easy to verify. Then we assume it's true for some arbitrary n, and show that it holds for n plus 1. If we can do this, we've proven the statement for all positive integers. Proof by recurrence, though a bit tricky, is a key tool for proving statements involving integers. It's like a mathematical domino effect, where proving one case triggers the truth of all the following cases. So next time you're faced with a statement involving integers, remember the power of proof by recurrence. It might just be the key to unlocking the proof you need. We've journeyed through the fascinating world of mathematical proofs. Let's take a moment to reflect on what we've explored. We started with the significance of proofs in mathematics. Understanding proofs isn't just about finding the right answer. It's about establishing why that answer is, indeed, the correct one. It's about building a robust, logical pathway that leads us unerringly to our conclusion. We then delved into the intricacies of mathematical induction, a method used to prove that a statement holds true for all positive integers. We learned how this method relies on two key steps, the induction base and the induction step, forming a sort of mathematical domino effect. Then we navigated the terrain of proof by contradiction. This method involves assuming the opposite of what we're trying to prove, and showing that this assumption leads to an impossibility, a contradiction. It's like setting a trap for falsehoods, catching them out in their inconsistencies. We also explored the realm of direct proof, the straightforward step-by-step approach to proving a statement. This method is like a well-planned journey, where every step is justified by logic and mathematical rules, and we ventured into the world of proof by recurrence. This method is particularly useful when we're dealing with statements that depend on integers. It involves establishing base cases and then using recurrent steps to build on them, like climbing a ladder one rung at a time. We've seen how these proof methods are applied in different branches of mathematics: geometry, number theory, set theory, abstract algebra, calculus, and mathematical logic. Each field has its unique challenges, and these tools of proof help us navigate them, uncovering the beautiful truths hidden within. As we wrap up this journey, let's remember that the beauty of mathematics lies not just in the answers we find, but in the way we seek them. The proofs are our guides, leading us through the labyrinth of numbers and symbols to the heart of mathematical truth. Remember, the beauty of mathematics lies not just in the answers, but in the proofs that lead us to them.